Hello, my name is Kyle Kaufman, and this will be my presentation for the artificial blood vessel design. Early designing of artificial blood vessels saw that the vessels themselves are made from biocompatible plastics and polymers with cells from the person's kidneys as a binding factor. They were used mainly for transferring blood out of a body to perform surgery, and they made for a quick use and were efficient, but lacked use of long-term usage during their processing. The choices for the models I had set to 5 millimeters diameter, as this was slightly above the lowest average blood vessel size and would act to give more apparent reactions, and each individual component would be therefore impacted more than compared to a wider diameter area. The flow rate that was used was averaged at about 8.05 kilometers an hour. This flow is above the average flow rate in comparison to the diameter vessel that I had chose. So this allows to show more of the effects that the flow rate has on the material. And the materials chosen were polyether polyol, PP copolymer, and nylon 101. These materials were chosen as they are biocompatible, thus recommended choices for bioengineering. The drawings for the three sizes are all very clearly identical to each other when looking on them, as it's a necessary component. And for the thickness of the vessel walls, I only put them at about 0.5 millimeters. This is the recommended size of the average vessel. So this is working with the vessels being very small for the flow rates, thus, as previously mentioned, allows for the example to be more present in the effects. And then having these drawings present makes it a lot easier to visualize where everything is and that all dimensions are indeed in millimeters. Starting out with the 1 millimeter, its stress and strain shows that both PP copolymers and nylon 101 both have very good reactions on their outer walls, as shown by how deep the blue is, showing that they had very little stress or strain on them. Meanwhile, their interiors are a lot more greenish to bordering on yellow, which shows that while the outside is handling the stress and strains very well, the interior still needs a bit of work on it. And in comparison, polyether has a lot lighter of a shade of blue on its exterior with greens matching, showing that the outer walls are getting more stress. However, the inner walls are a lot more balanced to the outer walls in comparison, thus showing that it's pretty well adjusted overall throughout the entire vessel rather than just the outside. Going to the 10 millimeters, this shows that the stress and strains throughout all three of the materials are actually relatively equal. Now, for polyether, this is a pretty good sign, as it showed very minimal amounts of change in comparison to copolymer and nylon 101. These showed a much greater change based on their increase in size and is further represented in how they react to being 100 millimeters. With 100 millimeters, all three of them are consistently pretty rough when it comes to the strain, while all are handling the stress very well. However, what should be noted is that polyether's reaction is a much more balanced. It changed very little and shows a lot more consistency in comparison to both. And that allows, and based on those results in the process, I believe that polyether showed the most promise. 1 millimeter was average in comparison to PP and nylon, but a bit worse overall, but had a lot more consistency. 10 millimeters, the increase actually was more consistent. The pressure overall did not affect it as much and allowed for the flow demonstration to be more equal to the others. And at 100 millimeters, it had a much higher breaking point, but its results were very similar. And then with polyether, it is also a very highly recommended material. Based on my research, it was a proper biocompatible, and further developments showed that its price is actually going down over the years. It had a spike earlier, but it's consistently been going down, making it a wise investment in the future. And then final mentions, the system used allowed for a balance of understandable but difficult steps. The proper usage, such as the visuals and stress, may be altered when it's actually done in the real world instead of a simulation. And then, as noted, simulations can vary from the actual counterparts. And for further example, the simulations might have run better if the diameter was bigger to allow more of the flow to go through, and then lowering the flow to match the diameter may also have resulted in better changes. This was my presentation, and I thank you for listening, and I hope you have a wonderful day.